So today in this video, we're going to talk about complex zeros and linear factorization. So how can we find all of the zeros of a function, the real and the imaginary zeros, and then write out a linear factorization? So the first thing we're going to talk about is the conjugate zeros theorem. So some things to think about first. Here we have f equals x squared minus, or f of x equals x times x minus 2 times x minus 3i, and then g of x equals x minus 3i times x plus 3i. So both of these have imaginary roots. We want to factor these out or FOIL these out and see what we get. So if we start with this one, we get x squared minus 3ix minus 2x plus 6i. So you'll get x squared. And then we have these two are the x parts. So minus 3i plus 2x plus 6i on the end. Then we can multiply these out. You'll get x squared minus 3ix plus 3ix minus 9i squared. Those will cancel, and then this will become positive 9 because I squared is negative 1. So you get x squared plus 9. So they both start out with imaginary portions, but this one ends up with just real numbers, and this one has a whole mess of imaginary numbers. So you want to think about why does this one not have imaginary coefficients? The reason comes from this one has two conjugates. So the conjugates cancel each other out from the last video. So that's all the conjugate zeros theorem is saying, kind of. So it says if a polynomial with real coefficients, so it's something like this, where we don't have any imaginary numbers in the polynomial, has a complex zero, then you have to have that conjugate also be a complex zero, so it cancels out the imaginary parts. So if you have x equals 3i, you also have to have x equals negative 3i. Or if you have x equals 2 plus I, x also has to equal 2 minus I. So you get both of those options. So how can we actually use that? So here we want to find a polynomial with real coefficients that has zeros at 2 and x plus 5i. So this also means that 1 minus 5i is a 0. So we actually have 3 zeros here. So if you write this out, we know x minus 2 is a factor, x minus 1 plus 5i, and then x minus 1 minus 5i is a factor. And now we're going to FOIL and expand this whole thing. So x minus 2, I'm going to distribute this negative n right here into my factors. We get x minus 1 minus 5i, x minus 1 plus 5i. And then you don't have to do it this way. I would recommend multiplying these two imaginary parts together first so you can get rid of it. So you're not multiplying two chunks with imaginary numbers, but you don't have to do that. You could do the x minus 2 into it first. So this is going to get a little messy. We'll do x minus 2 here. And then I'll do different colors so you can kind of see what's going on. So this one has to go to all three of these. We'll get x squared minus x plus 5i x with that one. We'll do negative 1 with this one, so we'll get negative x plus 1 minus 5i. And this chunk, you'll get negative 5i x plus 5i minus 25i squared. Okay, so lots of things here. This will cancel with this one. This one will cancel with this one. And then this becomes 25 because I squared is negative 1. So if we rewrite this out, we have x minus 2 and then x squared. And we have this x and this x give us negative 2x. And then 1 and 25 to give us 26. And now you need to FOIL this out one more time. So multiply again, we get x cubed minus 2x squared plus 26x minus 2x squared plus 4x minus 56. Combine all of your terms, and you'll get x cubed minus 4x squared plus 30x minus 56. And that will be your polynomial. As a note here, if it's asking for a polynomial with real coefficients, you want a function, you have to put a y equals, otherwise it's just an expression and you're not answering the question. So make sure you have this y equals, otherwise I'm going to take a half point off on your test because it's no longer a polynomial, you're just writing an expression out. Okay, the zeros theorem in linear factorization. So if we look at these, we can find the zeros of these, and then we're going to use them later, so write them down somewhere you can see them. This factors into x minus 3, and this is x plus 1. So we get x equals 3 and x equals negative 1. This one here, you can't actually factor, so you're going to have to use the quadratic formula, which you may not have been doing for a long time. So that is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So make sure you have that memorized to use, because we'll be using it quite a bit. So for this, a is 1, b is negative 4, c is 13. So if we write this out, x has to equal 4 plus or minus the square root of 16 minus 4 times 1 times 13, all over 2 times 1. Simplify this. Inside the square root, we end up with negative 36 over 2, which then you get 2 plus or minus 6i. Oh, this should be 4 right here. Divide everything by 2, and you get 2 plus or minus 3i. So if you can't factor, you can do the quadratic formula. The quadratic formula will always work. So even if you did it on this one, you'd get these two values. It's just more effort than factoring. So if you can factor, factor. If you can't, do the quadratic formula. Okay, so the zeros theorem says a polynomial of degree n has exactly n zeros, provided you include complex zeros and you count the multiplicity. So if you have a degree 8 function, you'll get 8 zeros. You might have 2 imaginary zeros. You might have x equals 0 3 times, but you're going to have 8 different zeros to add up to the degree of your polynomial. So here's kind of an example. We have this function, right? And it was right here. We had one spot that it touched. What that means is somewhere over here, so if we had our x-axis here, we would have had 2 zeros there. These up here are going to be your imaginary zeros. So they're still here, they're just imaginary. So you can find them using like a similar thing we did before, with like factoring out and dividing out stuff. So a linear factorization uses the zeros theorem. So the zeros theorem says that a polynomial can be factored completely using all of those zeros you found, the real and complex ones. This is called a linear factorization. So it's just writing out all the factors. And we'll do some examples. So here is our same polynomial from above. We want to write the linear factorization. All that means is factor it as far as you possibly can until there's no x squareds left. It's just x's. So if we factor this, you get x minus 3, x plus 1. Nothing can be factored any further. You only have x1s. You can see all your zeros from this. So this would be the linear factorization. Okay, now we're going to do this one. This one again is the same one we had before. So the zeros we had found were 2 plus or minus 3i. And that came again from doing the quadratic formula. So if we're going to write this one out, we have x minus 2 plus 3i. And then we have x minus 2 minus 3i. And then you want to distribute your negative n and we'll get this. So this would be your linear factorization. It's factored completely out, there's no x squareds in it, and you can find your zeros from this. Okay, so if we keep going here, looking at this, we have that 2/3 is a zero. We want to write the linear factorization of this function. So first off, you want to find all of the zeros so you can actually write those down. So I'm going to start by doing division using 2/3. And here we have 3, -14, 47, and -26. Drop the 3 down, you'll get 2, -12, -8, 39, 26, and 0. And again, check to make sure you actually get 0 to make sure you're doing everything correctly. Okay, from here, we can rewrite this out. We now have f of x equals x minus 2/3 times 3x squared minus 12x plus 39. And now to simplify this, I'm going to take a 3 out so I have smaller numbers. So we get 3x minus 2/3 x squared minus 4x plus 13. And then this, again, to use the same thing, is what we had up here with these zeros. So you can do the quadratic formula to find those again, but since we already did it once, I'm not going to do it again. You'll get 3 times x minus 2/3 times what we had before, so x minus 2 minus 3i, x minus 2 plus 3i. And you can stop here. One thing you can do to make it a little bit cleaner is you could distribute this 3 into this first one. So your other option would be 3x minus 2, and then this x minus 2 minus 3i, x minus 2 plus 3i. But either one of those would work as an answer. Okay, so here's one more. Try this one, pause the video, and then we'll talk about it. Okay, so do 1/2. We have 2, 3, -8, and 3. Drop down the 2. You'll get 1, and then 4, and then 2, -6, and -3. Works out to 0 like you want it. If we write out what we have so far, we have x minus 1/2, and then 2x squared plus 4x minus 6. You can factor a 2 out of this one to get 2x minus 1/2, x squared plus 2x minus 3. And then we can factor this again. This is the same one we've already done. So you'll get x plus 3 and x minus 1. And then again, you could factor this or distribute this 2 back in to get 2x minus 1. If you don't, that's fine. It's just a little bit neater mathematically to put that in. But you can do either one of those. And your homework is a worksheet on Schoology.